Welcome to Brain Vision.
Okay, so the mass of the sting that has entered can be determined by the final mass minus the initial mass, which is m2 minus m1. And we know the final mass can be equal to volume divided by the final specific volume, and the initial mass can be equal to the volume divided by the initial specific volume, since we know the volume in this case is constant. So we should have V times 1 over V2 minus V1. So if you take a look at the table A5, which is the saturated water pressure table, at 1 megapascal, the corresponding specific volume is 0.19436 meter cube per kilogram. And then let's take a look at the table A6, which is superheated water table. So at 2 megapascal, 300 degrees Celsius, the corresponding specific volume is 0.12551 meter cube per kilogram. And we know the volume from the question is given as 2 meter cube. So now let's plug in back to the equation to determine the mass of sting that has entered. So we have Ma is equal to 2 meter cube times 1 over 0.12551 meter cube per kilogram minus 1 over 0.19436 meter cube per kilogram. And this will give us the mass of the sting that has entered is about 5.645 kilograms. So now let's take a look at the next question, which is the question for the pressure of the sting in the supply line. So first we need to set out such energy equation here. So we have E in is equal to delta E. E in is the energy that was entered into the tank, and delta E here is the change internal energy in the tank. If we expand it, we have M in times H in is equal to M2 U2 minus M1 U1. M in here is the mass of sting that has entered, and H in is the corresponding enthalpy. Okay, and M2 here is the final mass, U2 here is the final internal energy, M1 is the initial mass, and the U1 is the initial and internal energy. So in order to determine the pressure of a sting in the supply line, we have to determine the enthalpy of the sting in the supply line, which is the corresponding enthalpy here. So we have H in is equal to M2U2 minus M1 U1 over Ma. So we know final mass is 15.935 kilograms. Initial mass is 10.29 kilograms. And we know the mass that's entered is 5.645 kilograms. And if you take a look at the table A5, which is the saturated water pressure table, so at 1 megapascal, the corresponding internal energy is supposed to be 2582.8 kilojoule per kilogram, since it's a saturated water vapor. Okay, so you need to look at the corresponding internal energy along the water vapor sections. Okay, and then now let's go to the table A6, which is the superheated water table. So at 2 megapascal, 300 degrees Celsius, the corresponding internal energy is 2,773.2 kilojoule per kilograms. So now we can plug in back to the equation to determine the enthalpy of the sting in the supply line, which is equal to 3120.27 kilojoule per kilograms. So now we know the enthalpy of the sting in the supply line. So therefore, we can just use the table to try to find the pressure of the sting in the supply line. But it seems like if you take a look at the table, you can't really find such enthalpy with the corresponding pressure. So therefore, we have to use the interpolation in this question. So if you take a look at 400 degrees Celsius in a superheated water table, which is table A6, you can tell that 3120.27 kilojoule per kilogram is lying between 3118.8 kilojoule per kilogram and a 3139.4 kilojoule per kilograms. And if you take a look at 400 degrees Celsius and 39.4 kilojoule per kilogram for the enthalpies, you'll find that the corresponding pressure is 8 megapascal. And then at 400 degrees Celsius, 3118.8 kilojoule per kilogram as the enthalpies, you'll find that the corresponding pressure is 9 megapascal. So therefore, we can use the interpolation to determine the pressure of a steam in the supply line, which is such equation here. So eventually, we'll have the pressure of steam in the supply line is approximately equal to 8.9286 megapascal. And these are the answers for this question.